2017 Leaving Cert High Level Question 8, Paper 2 is Statistics. And it's based on 15-year-olds in Ireland. Their weights are normally distributed, which they always will be in these questions, which gives us this bell curve. So the mean is 63.5. That's in the middle here, the mean. And the standard deviation is 10. So 1 standard deviation, 2 standard deviations, 3 standard deviations. You're 68, 95, 99.7. But in this case, we're given more information that we're not using the empirical rule, which is what this is. We're told that Marissa is 50. Find a percentage who weighed more. A sketch always helps in these questions just to see where we're at. So I've got my average in the middle, 63.5. So she's down here somewhere. 50, she's more than 1 standard deviation away. So there's going to be quite a lot of people heavier than her. So if we put this into the formula x minus mu over sigma, we will get her weight x. X is my test statistic. So what are we testing? 50 kilos. Minus the average, 63.5, over the standard deviation of 10. And this is going to give 13.5 over 10, which is 1.35. So we need to go to the z-score tables, and I'll just jot down what you should see. This is the 1.3 in the z-score tables. We're looking for 0.05. 0.04 is 9099, and 0.55 is 9115. So that would mean we only ever, in the z-score tables, they're only giving us the positive numbers. We can see we actually have a negative here. I should have wrote negative 1.35. So we're only looking at this side of it, but it's symmetrical. So what they're giving us the answer to is if she was over here, that there would be 91%, what is it, 91.15% of people to the left. So it's the same going this way. There's going to be 91.15% going to the right, which are heavier than her. So 91.15% are heavier. In part 2, we're told Kamal is 15 and 1.5% of 15-year-olds are heavier than Kamal. Okay, let's have a look at the little diagram. We're asked to find Kamal's weight, so we need to go back and find x. So here's Kamal. There's 1.5% of people in here. So what that means is in here there are 98.5% of people, which is what the z-score would be if we were going from the start to the finish like we did in part 1. So we need to work backwards. We need to go to the z-score tables. 98.5% is 0.985. And you should see it's at 2.1. I'll put both values down just so you can see either side of it. 2.17 is 9850. 0.07 and 0.06, just the one beside it, 9846. Sometimes the values in between these two numbers, you could round it off, or you could take the midpoint of 6 and 7 or whatever value is closer to it. But in Leaving Cert match, you don't really need to do that. You can take whatever value it's closest to. So 2.17 is the z-score. So what equals 2.17? X minus 63.5, the same as we had previously, over 10. Just look up at the previous one. X minus mu over sigma. So we just simplify this down. X is going to be equal to 21.7 plus 63.5. Or you could write X minus 63.5 and then bring it across. But if you can see what to do in two steps in one, may as well do it. So 63 and 21 is 84, and 1.2 is 85.2 kilograms. So that's Kamal's weight. Next part of this question, in 2016, so the following year, 150, so we have a sample of the 15-year-olds were randomly selected and their weights recorded. They were normally distributed with a mean of 62 and standard deviation 10. Test the hypothesis at the 5% level of significance, so a 95% confidence test, that the mean of the weight had not changed from 2015 to 2016. State the null hypothesis and your alternate hypothesis and give your conclusion in the context of the question. So there's a couple of ways to do these questions. I'll do it both ways to show you. The null hypothesis is what they're asking us to test, and we can just say H0 equals weights not changed. So H1, the alternate hypothesis is that weights, very simply, have changed. You don't need to go into too much detail here. So we're looking at 150 students. So my N is equal to 150. I still have my standard deviation is 10. I have my mean is 62. And we're seeing, has this significantly changed? So I'm going to do a confidence interval first. Confidence interval. And I'm just going to show you where the 1.96 comes from. So there's a 1.96 in this question. So if we just have a quick sketch and we say 95% confidence, the 5% level of significance would mean that in here, there's 95% overall in the middle, which means that each tail has 2.5%. So if you go to the Z-score table and go to 1.9 and go to 0.06, you're going to see 9750. And you can see here that that's 97.5%, which will be the total from this line all the way back. But we're looking in the middle part, so there's 2.5% in each tail. So 1.96 represents 95% when we take in the two tails. So it's the middle part. This confidence interval in here is 95%. So we can set up our confidence interval as 1.96 by sigma over the square root of n. And this will tell me in relation to my 62 how much the weights have actually changed by. So 1.96 by 10 over the square root of 150. Just type this into a calculator. It gives us 1.6003. Well, we'll just take the 1.6003. We can eliminate that bit. So let's look at our 62. So if I add 1.6 to my 62, I get 63.6. So this is my interval. We can say with 95% confidence the weights are between these two values. 62 minus 1.6 is going to give me 60.4. And we set up our confidence interval to say between 60.4 and 63.6. We can say with 95% confidence the average weight are between these bands, or these values. So now let's go back up and check our previous average weight. Our previous average weight was 63.5. You can see it here. So is 63.5 within this band? You can see just about 63.5 is just about in here. If it was outside, we would say the weights have changed. 63.5 is inside. Therefore, we can say with 95% confidence that the weights have not changed, or that average weights have not changed. So we then accept our null hypothesis was that the weights haven't changed. So we accept H0, and you have to write this at the end, accept H0, reject H1. And that's one way to do it. So another way to do it is to use my standardizing formula, which is what we use in part 1, my standardizing formula, which is x minus mu over sigma. But I also bring in the standard error of the mean. And these are in the tables. And the standard error of the mean, when we're dealing with samples, is sigma over the square root of n. So I just plug my values into this. Instead of having sigma over root n. So I'm going to plug my values into this x minus mu over sigma divided by root n. And if my values are outside this plus or minus 1.96 range, we can go through the same process of accepting or rejecting H1. So let's test our 62. our new average, against 63.5, and we're dividing that by 10 over the square root of 150, and typing this into a calculator, we get minus 1.837, and you can see that that's inside my range. So you could say inside plus or minus 1.96, and you can see it's pretty close to the edge of it, which is what we got in the previous part. So it's inside that plus or minus 1.96. Go through the same process then of stating accept H0, reject H1, and all the jargon that we had earlier. So two different ways to do your 95% confidence interval, or your 95% hypothesis test, and create a confidence interval. The next part of this question is this tree diagram for it raining in Galway. You're told in Galway it rains in the morning on 1/3 of school days. And if you're from Galway listening to this, you'll know that that is not true. It rains every day in Galway. When it's raining, the probability of heavy traffic, which is this one here, or HT, is 1/2. And these values are given to you in the diagram here. When it's not raining, the probability of heavy traffic is 1/4. This one here. That's that one. Rain, heavy traffic, late is 1/2. Rain, traffic, late is 1/2. It's that one there, or TL. Or heavy traffic is what they're calling it. And also that's also another lie. The heavy traffic in Galway is every single day for the past 30 years. The last one, when it's not raining, no heavy traffic, and late is an 8. Not raining, no heavy traffic, late is an 8. And then it gives us this one other piece of information. In any other situation, the probability of being late is 1/5. So there's one there that is this guy here. This L here wasn't given to us. So that one's going to be 1/5. So we put these in. So if it's 1/2, if the probability is 1/2, the other side of it has to be 1/2. So we can fill in these values. 1/5, the other side of that is 4/5. They always add up to 1. So 1/5 and 4/5, 1/4 and 3/4. We got the top half done, we do. Bottom one, nearly 3/4 and 8, 7/8. So now it's a case of going and writing these sums out. So the first one is 1/3, this 1/3 here, by 1/2, by 1/2. 1/3 by 1/2 by 1/2. The next one is 1/3 by 1/2 by 1/2 as well. The next one is 1/3 by 1/2 by 1/5. And then obviously it has to be 1/3 by 1/2 by 4/5. I'll write the answers in a minute. The next one is, I didn't fill this one in, actually I left this one out, 2/3 down here. So 2/3 will be the first value for them all, if you want to do it like this. So 2/3 by 1/4 by 1/5, that's this one. Then we have 2/3 by 1/4 has to be by 4/5. 2/3 by 3/4 by 1/8. So 3/4 and 1/8, and then obviously the last one has to be 7/8 at the end. 3/4 by 7/8. Okay, so let's fill in our values. 3 by 2 is 6 by 2 is 12, so 1/12. Next one, I wrote it. Did I write a 5th there? I meant to write it. Oh no, I haven't gone all the way up. The first one is 3 by 2 as well, by 2, which is a 12th. 3 by 2 is 6 by 5 is 30, so that's 1/30. 3 by 2 by 5 again is 30, but we have a 4 on top. We have a 2 on top this time, and we have 3 by 4 by 5, which is 60. 2/60 or 1/30. I can write as 1/30. We have a 2, when the 4's cancel, make it simpler for ourselves. So we have a 2 on top and we have 3 by 5 on the bottom. So that's 2/15. Cancellations here, my trees. So I have a 2 on top, 2 will cancel, make it a 1. The 4 make it a 2. So it looks like 1/16. And then the bottom, have I any cancels? The trees. 2 goes into the 4 once, which leaves 7 on top. And is that 8 on the bottom? No, I made the 4 2. Just be careful. 7 over 16 on the bottom. B part 2, you're asked quite simply, on a random school day, what is the probability of being late? So I have my 4 lates. I've got my 1 over 12, my 1 over 30, my 1 over 30, and my 1 over 16. So 1 over 12 plus 1 over 30 plus 1 over 30 plus 1 over 16. I'm just going to type this into a calculator. It's coming up as a simple fraction, 17 over 80. The last part of this question, on a random day in Galway, find a probability that it rained in the morning given that you are late for school. So this is your conditional probability. I'll just write P for probability. So conditional probability, the probability of say A given B is equal to the probability of A intersection B over the probability of B. So if we fill this in order, on a random day in Galway, find a probability that it rained in the morning given you were late. Well, here's rain in the morning, and these two are the lates. So that's the intersection part on top. That's rain in the morning and late is 1 over 12 and 1 over 30. So 1 over 12 plus 1 over 30. And the probability of B is that it rained. That's what we got in the previous part. Was the probability of, no, the probability that you were late, given you were late, is the second part. So that's the probability of B, 17 over 80. Just type this into your calculator. Another simple fraction, 28 over 51.